Thank you. It's a great pleasure to be here. I feel like I'm one of the oldest people in the room. So let's see whether an old guy can teach you young dogs some new tricks. I want to tell you about a new way to learn. And I'm hopeful that we'll move beyond this horrible big data-based notion of AI and learning which plagues us today. So let's dive in. To me, there's a very compelling number here, and that's this 5 billion number. Okay, can anybody tell me what 5 billion is? Okay, I'll tell you the number. It's the number of cores that ARM ships per quarter. Okay, so just ARM is shipping 5 billion cores a quarter. That's 20 billion a year. If you take them and all the other device vendors, that's a lot of devices. So a really interesting question is, how are these edge devices going to get smart? Are they going to get smart by sending the data up to the cloud? Yeah, I tell you, Amazon and Google and Microsoft would love that. I'm here to tell you that there is another way. These devices will get smart the way you get smart, by wandering around, making experiments, and learning on the fly. Okay? The technology generally is called incremental learning, and I encourage you to go and look at it afterwards. You can dig into my materials. I have some URLs, but please feel free to follow up with me by email. So the cloud-based approach, big data learning, we're all living in this. We're still digesting this big data Hadoop thing, which came out of Google 10, 15 years ago. Yeah, whatever. I get it. It's fine if you're Google, but it's not so cool if you're on the edge. Too much data. Rest is the world's biggest problem. Everybody knows what rest is, right? Tell me. By the way, whenever I talk to people, feel free to stand up and yell and tell me I'm stupid, because it makes more fun for everybody else. And these streaming data pipelines, for example, Flink and Beam and Spark and so on, which are up in the cloud, they're all awesome. It is the world's greatest corpus of machine learning tech, but for most people on the planet, it's a big, big mystery. So, training in the cloud, inference at the edge. It's the approach which is being pushed by Amazon. It's being pushed by Microsoft now. Yeah, cool. Who's going to build this model? Do I have to build a model for every little thing? What if I move the thing 10 yards further down the road? Will it still work? Okay. And this is a huge, big problem. How is the model distributed to the edge? Are the models robust? And so on. And it turns out that they're highly variable. Gosh, we know that because we live in the real world. Okay. So let me tell you a new model. The intelligent edge is one which analyzes and learns and predicts from time series data an evolving worldview on the fly. Much as you do. To know what you want to eat for breakfast, I do not need to watch the movie of every breakfast you've ever eaten. You know what you want for breakfast. That's it. Okay? So how do we get there? I divide the world into two. There's new stuff, like the new smarter devices with richer cores and more memory and so on. And there's the old stuff. But every single one of these things can develop a digital persona, a digital twin, as it were, of the real world of itself, and relate itself to things around it. In other words, building a graph. If you're familiar with any of the graph databases and so on, build this database, which is essentially this evolving worldview graph on the fly from experiential data. Okay? These digital twins, these digital personas, can collaborate to analyze, learn, and predict the future in real time. I'm going to give you some examples. And then, we just make this information available via the good old API, or if we're in some operational context, perhaps using a user interface to a human. So here's an example. A small city in the US, Palo Alto, California, delivers more data per day than all of Twitter. Okay? Lots. So go to a big city, you're drowning. I just need something small, a $200 NVIDIA Jetson device, which is a 64-bit ARM and a small GPU, 256-core GPU, to do something totally awesome. I can route a Waymo through the city and it will never stop. That is, the digital personas of each one of the intersections can predict far enough out what it is going to do, what the traffic is going to do, that I know exactly when the phase of each light will be green, and my Waymo never needs to stop. Okay? And I can do that on massive amounts of data. So Palo Alto is 4 terabytes, so it's actually much more than that now. Now, if I solve this problem in the cloud, AWS, even losing Lambda, I'm looking at $5,000 a month. And I showed you that I can solve that problem. Actually, I could solve most of the San Francisco Bay Area's problem on NVIDIA Jetson for $200, once off, done forever. So message 1, don't be hoodwinked by the cloud guys. Moore's law serves the edge just as well as it serves the cloud. Okay? There is tons of local cool CPU, and you can do smart things right here. Okay. By the way, at $50 per intersection per month, it's not worthwhile solving these problems. But if I can do it for pennies, everybody and their dog wants to buy the data. They want to buy access to these insights from Uber and FedEx and so on, all the way down to Apple, Google, and the insurance vendors. Okay, so there's tons of cool insights to be had for nothing. A couple of Raspberry Pis. Anybody doesn't know what a Raspberry Pi is, just a little ARM device to track and map millions of RFID tags in real time, put them in 3 space, and then watch up components of an aircraft being built. Okay, just radically cutting in half a data center to do this in a couple of Raspberry Pis. And how do we get there? Okay, and the cool thing is, everything to get there is available to you right now. It's just a different way of looking at the world. Okay, so the problem right now is, I'm going to put the problems in a couple of buckets. REST. Why is REST my problem? REST is awesome for scaling out the web in the cloud. Yeah, everything's stateless. It's brilliant. It means things can fail, I can load balance, I can do all these cool things. But REST, when I'm dealing with large amounts of frequent transactional data, every time I hit a thing, I have to go and hit another REST-based database, load the old state, pull in the memory, do a bit of compute, stick it away again. Hey, I'm looking at 100 milliseconds. Whereas if I did it at the edge, yeah, do it in memory, nanoseconds. If I get 10 billion CPU cycles per REST transaction, I can do a lot of learning in that. Second big problem, big data. The vast majority of data at the edge is of ephemeral value. You just don't care that the traffic light was green at 8:07 and 15 seconds last Tuesday. You just don't. But it's useful in terms of prediction. So learn on the fly, okay? And then the other one, this big sort of atomic sign, is all about needing a data scientist to solve these problems. Yeah, this is all about turning devices into the data scientists. Okay? Avoiding that whole problem, because very few people have got the data science skills to build these complex models. So what am I going to tell you about? I'm going to tell you about 2 technologies. Really, the first one you know about, you might know it by multiple names. Your devs, so reactive. Anybody know what reactive is as a paradigm? Akka, anybody know Akka? Yeah, you know Erlang, these paradigms, okay. Little local stateful things which do stateful computation wherever they happen to be, and they're really fast. That's cool. And the other way is this technology, which I encourage you to learn about, which is essentially incremental learning, which has taken massive strides forward in the last couple of years. Okay, so REST and big data, costs going up. You don't know when to throw the data away. This cost for doing these cheap things at the edge is way small. In fact, my biggest problem as a startup guy is actually, if I'm selling a thing that runs on a Raspberry Pi, outright charge you $1 million. Okay. Slow. I don't like this batch-based notion of learning, okay? Batch and semi-batch, why are we doing that? Let's learn on the fly, okay? And so experimentation and learning lets us continually make hypotheses and refine them and get better. Okay, and then skill set wise, I don't need all of these people that are chained together, these big pipelines plus a data scientist. I just need some awesome people like you, devs. Okay, so let's dive into this. So what is this notion of a digital persona? In fact, the distributed actor model is what I'm talking about. Well known from Erlang. There's nothing new here. This stuff's been around for 40 years, okay? That's why I know it. So here's the idea. Some traffic light turns, and then what am I going to do? I'm going to make all these REST calls up in the cloud, and everything changes, right? All of these are 20 milliseconds of REST and JSON and God knows what else. Instead, by the way, the traffic light changes, or actually most old stuff just continually says stupid things to you, and so you end up doing a lot of wasteful stuff. If you're looking at a city, smart city infrastructure, actually most city infrastructure is not going to change in our lifetimes. It's very noisy, it's full of horrible stuff, and we can't do this, okay? We can't evolve the cloud by continually modifying state in databases. Databases are not our friends, okay? The model, which is better, it's say, yeah, whatever, the cloud is useful for some things, we'll use it when we need to, but on cheap devices at the edge, so a ruggedized Raspberry Pi or something, gosh, all I need to do, sorry, forget the slide, all I need to do is build a little digital personality for each thing which is talking to me, okay? And let it be the data scientist. So instead of going through this complex modeling lifecycle of trying to figure out and clean up data, let these little digital personalities of things clean up their own data and do the right thing, learn on the fly. Form models, form relationships to other things around them. So let's do this in a model style which is familiar to you if you're familiar with the distributed actor model or Akka or one of these frameworks. This is what it would look like, reactive style. So you could do this today in Akka on a Raspberry Pi. Okay, light says I'm green. You say, I don't know what that light is. Cool, I'll make a new one. It's an actor. It's a tiny little lightweight process sitting in memory someplace. And all I do is change one memory location. Gosh, that took me all of 10 nanoseconds. Pretty quick. Pretty quick. I didn't have to go to the cloud to do this. And then it says, oh, I'm red, and I change it. Cool. And I throw away the original data. And so all I've done is change one little memory location, and I'm done. And so this little digital personality for a light is a trivial little thing which you could write in 5 lines of code. Okay? And when it continually says I'm red or it continually does something stupid, who cares? All you're doing is taking an interrupt on a little cheap ARM device at the edge and checking some state. Okay? So this notion of reactive is very familiar if you've ever written device driver. It's like deal with stuff which is stateful right here, have state in memory right where the data is, and yeah, it's not a big problem. REST is not my friend here. Okay. By the way, REST is definitely not my friend in this world. Okay? So in Palo Alto, we have, whatever, several hundred intersections, all of which are chirping. Several hundred sections, each of which has got maybe 50 or 60 sensors. Every single one of them is chirping every second. And New York City is way worse, okay? It's way worse than that. So I want you to believe, and if anybody doesn't, feel free to raise your hand or throw something at me, that it's very simple, using a framework such as reactive, to create digital actors, personalities, digital twins of these things, which process their own data at the edge in memory really fast. And we throw away the data. Notice I haven't hit a single REST interface yet. I haven't hit any big data store. And by God, I don't need big data to do this. Now, each one of these digital twins represents the current state of the thing. Okay, so the light's red. Great. Well, what about the past? Can these things learn? Okay, so the key point I'm trying to make, it's a short presentation, so I'm going to fly through this. One, you should have got this idea. Actors at the edge save time because I don't need to do this REST and big data thing. Okay, got it? Cool, let's do the learning piece. Well, now I have all these digital twins, great. All my traffic lights, they all have their all my intersections. They have the current state of every sensor on them. How do I make that useful to me? Well, it turns out that in the edge, there is really a ton of local contextual information, which you very seldom have in the cloud, or at least you'd have to know it for every single application in the cloud, which makes the graph build itself. So if I said every intersection which is trying to predict its future, it radically improves its accuracy by knowing what's going on with the traffic lights around it. You'd say, duh, that's pretty obvious. Cool, so what I need to know is the lat and long of every one of those intersections. It's part of the database, it's how they report to me, and hey presto, I've built the graph. And then the next thing, which is telling an intersection to learn on its data using incremental learning by using not only its own data, but the data of the people immediately around it, say within a 1,000-yard radius. That's all I have to do to solve this whole problem. I didn't need a data scientist or anything else. We're done. Okay? And now I need an algorithm which can deal with incremental learning. And I apologize for having to go fast, but that's just the way it is. How do we do this? Incremental learning is this way of experiencing the world. So I have a rapidly evolving worldview where I have lots and lots of samples. I start off making random guesses. All the weights of my DNA are just random. Okay? I predict something, I compare it with the way the real world evolved, take the difference, and backpropagate it. And do it again, and do it again. But the cool thing is I can track the error. I can track the error and see if this thing is diverging or converging. And if it diverges, yeah, I'm out of luck. If it converges, which a very large number of things do, and there are lots of algorithms you can replace on the fly if you want to get better at this, then you get better. And as soon as your convergence is good, you're done. So what do you have to do as a developer? You had to say, oh, if you are a digital twin of an intersection, this is what you do. You take your data, and you throw it into a DNN, you take the data from your neighbors, you throw it in with that, and you're done. Did I need a data scientist for that? I don't need a data scientist. I'm going to fly through one more example, which is not necessarily machine learning based, and you'll get the idea. We do this funny thing, tracking RFID tags for a vendor which is making military aircraft. And so they have millions and millions of these RFID tags, and of course they're paying through their nose to Oracle, right? My next worst enemy, okay? And why are they paying Oracle? Because every time an RFID tag gets seen by one of 2,000 sensors in a couple of kilometer long assembly plant, you have to write an RFID tag read into a database. And then at the end of the day, they're trying to figure out where the heck are all the things. It's hard. Very expensive, computationally intensive. But if I just create a digital twin for every tag, the first time I see a tag, I just create a digital twin, and then hand it its own data and say, process it, it looks like this. It's trivial. A couple of Raspberry Pis, 4 gigs of memory each, and then whenever a tag gets seen, the logical reader says, hey, I just saw you, and here's the RSS, which is the signal strength. Okay? So tag just updates its state. It gets seen by lots of readers, and so what does it do? It learns, and it's trivial. This one is really trivial. It learns the distribution of signal strength, and it places itself in 3 space. So suddenly every tag on a Raspberry Pi is learning where it is in 3 space by triangulating off the readers. And so I can go to any one of these tags, because it has an API, and I can just say to it, hey, where are you right now? More than that, I can say, tell me all the things that are within 3 meters of you. Okay? And I can start to look for wheel subassemblies, etc. Okay, so all I want to do is get across these key messages. As a user, as a developer, all you need to do is define the entities in the world, okay? The intersections, the sensors, and all these sorts of things, how they process the data, and how they are statefully managed, okay? Use a framework like Akka or whatever. Swim happens to be one of them, but you get the idea. This is not new stuff, okay? The streaming data that comes off the world builds these stateful models, which evolve very nicely through time, very cheaply. and it triggers computation. As new data arrives, you compute. And computation includes things like analysis, learning, responding to stuff, whatever it happens to be. Your application will depend on that. These twins can statefully analyze themselves, these little digital personalities which represent a thing. So every intersection or every RFID tag can analyze itself. But more than that, they can very easily locate themselves in a world of other things, given contextual information from the world that you are trying to represent. Machine shop floor or smart city, it doesn't really matter. Okay? And solve really interesting things in real time on not much compute. Okay? The most expensive thing you can rent in AWS is a GPU. Okay? You don't need this. You don't need this. I'm not an enemy of AWS. I just think we're wasting our time. Okay. And then you can deliver this by a streaming API or UI. Throw it into Kafka. I don't care. But the whole point is you can cheaply derive incredible insights using stuff you know already and deliver it to the world so people can build really powerful applications. Thank you.